All right, welcome to the Explainer. Today, we're not just going to talk about code. We're going to put it, and maybe you, to the test. I've got some real head scratchers for you, pulled from the world of Java programming. And these are the kinds of things designed to trip up even the absolute pros. So let me ask you, how well do you really know Java? I mean, sure, you might write it every single day, but the language has these little tricky corners, these dark alleys, that are specifically designed to catch even the most seasoned developers off their guard. So today, we're not going to sit around talking theory. No, we are going to run the gauntlet. And what I mean by that is a series of programming puzzles, ones that are actually pulled from real certification exams. And listen, this isn't about some obscure piece of trivia nobody cares about. These are designed to test your core, fundamental understanding of how Java actually works under the hood. Okay, let's dive right in. Each challenge we look at today, it's going to prey on a common assumption that a lot of developers have. It's all about testing what you really know about Java's mechanics. You ready? First up, we're diving into what I like to call the object identity crisis. We're going to explore what really happens when you make a copy of an object in Java. Because as you're about to find out, a copy isn't always, well, a copy.
All right, check this out. We've got an array list called original. We add a counter object to it, and that counter has a value of 10. Simple enough. Then we clone the list, creating a new list called cloned. Now here's the kicker. We reach into the cloned list, grab that counter, and change its value to 5. So the big question is, what's the value of the counter back in the original list? And the answer is 5. Yep, that's right. Changing the object in the cloned list somehow changed the one in the original. Now, if that just made you do a double take, don't worry, you've just fallen into a very, very common Java trap. So, what on earth is happening here?
This, my friends, is the shallow clone trap. See, when you call .clone on an array list, it does create a brand new list. But, and this is a huge but, it's a shallow copy. That means it only copies the pointers or the references to the objects inside. It doesn't copy the objects themselves. So both your original list and your clone list are holding references that point to the exact same counter object in memory. You change it through one door, it's changed for everyone. Okay, let's move on to puzzle number 2. We've got two string objects. str1 is core with a lowercase o, and str2 is co-re with an uppercase R and E. Then we have this one tricky line. System.out.println str1 equals str2. Pay very close attention to that single equal sign. So what gets printed to the console? The output is simply core. Not true, not false, not even the original core. So what gives? It's that single equal sign, the assignment operator. It's playing a little trick on us.
This is all about the order of operations and what an assignment actually does. First, the expression inside the parentheses gets evaluated. That's strung 1 equals string 2. That single equal sign means assign the value of string 2 to string 1. So string 1 now points to the exact same object as string 2. It's a reassignment, not a comparison. But here's the secret. That whole assignment expression itself evaluates to the value that was just assigned. In this case, that's the string core. So after the assignment is done, println just prints out that resulting value.
All right, let's switch gears a bit. We're going to move on to what we call deceptive control flow. This is all about code that just doesn't go where you think it's going to go. We're talking about the if statements, the loops, the switch statements, the very backbone of any program. And trust me, they have their own special set of traps. Okay, here's our next puzzle for you. It's a switch statement. The fruit we're testing is mango. Now, a couple of things to notice here. First, the default case is kind of weirdly placed at the top. But more importantly, look really close at the mango case. Something's missing. There's no break statement. So what is this thing going to print?
And the surprising output is mango. And then on the next line, banana. Yeah, both of them. So even though that default case was up top, the switch was smart enough to jump right down to the matching mango case. But the real story here is what happens after that.
The culprit, as you might have guessed, is that missing break statement. This is a classic feature or bug, depending on your perspective, of switch statements in Java called fall through. Execution jumps to the correct case, mango, and it prints mango. But since there's no break to tell it to stop, it just keeps on going. It literally falls through to the very next case, banana, prints that out, and then it finally hits a break and exits the switch.
Oh, here's a true classic. I think this one has probably bitten every single programmer at least once in their career. It looks like a simple if-else statement for checking a grade. But I want you to look very, very closely at the condition inside the if. It looks like we're checking if the grade is equal to 60. But are we really? What happens when you try to run this code?
The result is nothing. The code doesn't run at all. You get a big, fat compilation error. This isn't a bug you'd find at runtime. The compiler is smart enough to stop you before you even get that far. So why does it fail? It's that fundamental, critical difference between 1 equals sign and 2. Double equals, that's your comparison operator. It asks a question, are these two things equal? And it gives you back a Boolean, true or false. But the single equals, that's the assignment operator. It does something. The expression grade is equal to 60 first assigns the number 60 to the grade variable. And then the entire expression evaluates to the value that was assigned, the integer 60. An if statement needs a Boolean. It needs a true or false. It has no idea what to do with the number 60, so the compiler just throws its hands up and says, nope, type mismatch error.
Okay, for our last round of challenges, let's wade into the weeds of Java's standard libraries, its APIs. You know, these are the powerful, pre-built tools we rely on every single day. But every now and then, they have behaviors that are, well, let's just say they're unexpected, especially when you have multiple methods that all share the same name.
All right, here it is, our final puzzle. We have an array list of integers. We've added 100, 200, 100, and 200. Then we make this simple call, list.remove100. So the question is, what is Java doing here? Is it looking for the first object with the value 100 and removing it, or is it trying to remove the element at index 100?
And the kind of shocking result is your program crashes. It throws an index out of bounds exception at runtime. It doesn't remove a thing. It just blows up. And this is a fantastic example of why you really, truly have to know your APIs inside and out.
So what happened?
It's all because of something called method overloading. The array list actually has two different methods named remove. One of them takes an int as an argument, and that's for removing by index. The other one takes an object as an argument, and that's for removing by value. When you just pass the number 100, which is a primitive int, Java's rules say, I have a perfect match, and it chooses the remove int index method. So you think you're telling it to remove the value 100, but you're actually telling it to remove the element at index 100. And since our list only has 4 elements at indices 0, 1, 2, and 3, index 100 is way, way out of bounds and boom, exception.
So after all these little gotchas, what's the big takeaway? I mean, yeah, they might feel like tricky exam questions, but they really point to a much deeper truth about programming. Writing good, solid, professional code, it's about more than just knowing how to solve a problem. It's about having a really precise, deep understanding of the tools you're using every single day. And a core principle that helps prevent these kinds of surprises is something called encapsulation. You've probably heard of it. It's this idea of bundling data with the methods that operate on that data, and really importantly, restricting direct access to an object's components. You make your variables private, you hide them from the outside world, and you only expose them through public methods that you control, like getters or setters. It's about building a protective barrier, so you don't get those unexpected side effects like we saw with our clone example. It's a cornerstone of robust design.
And that really brings us to the end. You know, these puzzles, they were specific to Java, sure, but the lesson here is totally universal. Every complex system out there, whether it's a programming language, a piece of engineering, even a legal code, they all have these subtle rules, these little hidden traps that can catch you if you're not paying close attention. So I'm going to leave you with a question to chew on. What are the invisible rules, the tricky little gotchas that govern your own field of expertise? Think about it. Thanks for joining me.